what if we have more information about each of our students? And this is kind of inevitable, right? If you're implementing a program that's a database with people or customers or employees or anything else, you can imagine having a lot of data about anything you're representing in your program here. For the sake of discussion, suppose that every student at Hogwarts, of course, has a name. They have already a house, but they also have a Patronus. For those unfamiliar, this is the animal or entity that comes out of the end of their wand when they make a certain magical spell. The point here being is that we want to associate not just one thing with the student, but multiple things as well. Their name, their house, and their Patronus in this case. Well, what might code like this look like? Well, let me go back to Hogwarts.py, and let me start fresh for just a moment, and let me propose that I enhance this with a bit more data. And this data is going to look as follows. My students variable now, I'm going to propose we think of it as a list. What if we have a list of dictionaries as follows? Indeed, I want to literally implement this picture here. So notice that my previous picture just represented a single dictionary. But suppose I wanted to compose a list of dictionaries. That is, 4 students, so a list of 4 students. And suppose that each of those students is itself a dictionary, a collection of key value pairs, keys and values, something and something else. Well, here's one other way we can do this in code. Let me go back to VS Code here, and let me define a variable called students that is equal to a list. And I'm going to preemptively move my cursor onto separate lines because I know this is going to be long, and I want to fit all of the elements of this list inside of it. I'm now going to create a dictionary, one dictionary per student. And how do I create a dictionary? I just use those curly braces. But it's up to me to define what those keys are. And let me propose that one key this time won't be the student's name explicitly. It will literally be the word name, and they're going to have the name Hermione. This same student is going to have another key called house, and the value is going to be Gryffindor. And this same student's going to have a third key called Patronus, and the value of that is going to be, I had to look it up, an otter, according to the book. Now I'm going to create a second dictionary inside of this list. And again, a dictionary is literally like the human dictionary of words. It's a book that contains keys and values, words and definitions. What are the 3 words I'm storing in each of my dictionaries? Name, house, and Patronus. What are the definitions of those words for Hermione? Hermione, Gryffindor, and otter, respectively. For Harry, the definitions are going to be different in this new dictionary. Let me give myself another pair of curly braces and say this. Name, quote unquote, colon, Harry. House here is again going to be Gryffindor. And this one I knew, his Patronus is going to be, in this case, a stag. All right, next, a third dictionary. The name here will be Ron. And I'm going to go ahead and do that just like this. Next, I have the house, and he too was Gryffindor. Lastly, had to look this one up, Ron's Patronus was a Jack Russell Terrier. Lastly is Draco in a 4th dictionary now, so another pair of curly braces. The name of this student is, of course, Draco. The house of this student is Slytherin. And Draco, interestingly enough, at least according to the internet, has no Patronus, was never revealed in the books or the movies. So it turns out, this is actually a wonderful teachable moment, there is a special keyword in Python that is literally none, N-O-N-E, with the first letter capitalized. This represents officially the absence of a value. So I could a little sloppily do something like quote unquote, but does that mean I didn't get around to typing it or not? It's a little clearer semantically to say literally none, a special keyword in Python to make clear that I know Draco has no Patronus. It's not just an oversight on my part. Now that I have this, what do I have in the computer's memory? I have a list. How do I know it's a list? Because I see a square bracket at the beginning and another square bracket at the end. That's just my visual clue. OK, I don't know necessarily what else is going on here, but there's a list of something. What is in that list? Well, here too, the syntax is our clue. Because this line 2 starts with a curly brace and ends with a curly brace, I just know that is a dictionary. a collection of key value pairs. Now, this all fit on my screen perfectly, so I didn't bother moving all of the key value pairs onto new lines. It would have made it really tall, so I kept it all together here this time. But how many keys does this first dictionary have? Put another way, in Hermione's physical dictionary, how many words are in that dictionary? 3. The words are name, house, and Patronus. What are the 3 definitions or values of those words in Hermione's dictionary? Hermione, Gryffindor, and Otter, respectively. And the same story goes for Harry, then for Ron, then for Draco. I have, by design, chosen to give them dictionaries that have all the same keys, all the same names, but they all have unique values. And that's my design. That's my prerogative as a programmer. So why is this useful at the end of the day? Now I have access to a whole collection of interesting data about all of these students. And I can still do a loop. I can say, for student and students, that's going to allow me to iterate over this list of students. And let me go ahead and print out just one thing at a time. Let me print out the current student's name. So as complicated as the dictionary is, this should be pretty comfortable. For student and students is just going to iterate over every student in the list. 1, 2, 3, 4 total. The next line is just going to print out the value of the name key. It's like opening a physical dictionary, looking up the word name, and giving us Hermione, Harry, Ron, and Draco respectively from each dictionary. So if I run this version of Hogwarts and hit enter, there, I get all 3 of their names. But what if I want more information than that? I want both their names and their houses. Well, just add to print's arguments, student, open bracket, house, close bracket. All right, let's go ahead and run this. Python of Hogwarts.py and hit enter. So I now see Hermione Gryffindor, Harry Gryffindor, and so forth. Well, we can aesthetically clean this up a little bit by adding a separator with print, like a comma and a space, just so that when I run this again, I now see some commas separating these values. But recall that students have not just a name, not just a house, but also that Patronus. So if we want to print out that too, we now have the syntax via which to go into that same dictionary for each student and output their Patronus as well as their house and their name. So if I run this program one final time, now I see all of the data in this here dictionary. So this is a lot to absorb all at once, I'm sure. It's the last of our new data types. On top of lists, we have these dictionaries. But again, a dictionary at the end of the day is just a collection of values similar to these values here that allow you to associate keys with values. And the first version of this program associated literally the students' names with their houses. But then I realized in my next version, wait a minute, what if every student has not just a name and a house, but a Patronus? Let's actually standardize the names of our keys to be name, house, and Patronus. And then the values of those keys can actually be the data, like Hermione, Gryffindor, Otter, and so forth. Questions now on these dictionaries and iteration thereof?
I just was wondering if suppose the dictionary is very huge, and if I want to look up for a specific student, so how do I know where to look that student from? Like, can we sort it out in alphabetical order or numeric order or anything like that?
In short answer, yes. One of the features of Python is that it makes these dictionaries very highly performant for you. That is, even if they're very large, as they will be in future weeks when we manipulate more data, Python will find the data you care about quickly for you. And in fact, that is a feature of the language. That is a feature of a dictionary to get you the data quickly. And there are functions that you can use. You can sort the data. You can sift through it. You can do very performant operations, as we eventually will. Allow me then to propose, as we wrap up these loops, that we solve just a few final problems that will perhaps evoke fond memories of yesteryear, at least for me, wherein one of my favorite games growing up was this one here on the original Nintendo. And this is a two-dimensional world where the characters move up, down, and right, not so much to the left, in jumping over pyramids and obstructions like these. And allow me to propose that we use this just for inspiration, not to do something that's quite as colorful or graphical as this, but just to focus on, for instance, this barrier in the middle of the world here that Mario or Luigi had to jump over. And so this here seems to be like 3 bricks stacked on top of one another. And we won't do things quite graphically, but let's just implement a very simple Python-based version of this textually, using maybe just hashes for bricks. Because there's a pattern here, one on top of the other, and I bet we can solve this in any number of ways. Well, let me switch back over to VS Code here. And let me propose that we create a program called Mario.py using code in the terminal window. And then up here, let me start by implementing that same picture as simply as I can, printing out just literally the hash, and then the hash, and then a third final hash. This is going to be a very textual approximation of it, but I think if I run Python Mario.py, I've got a very simple version of that same column of bricks, so to speak. But you can imagine that certainly in a game where maybe the columns get higher or lower, it would be nice to write code that's actually a little more dynamic than that and doesn't just use print, 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 which is literally copy and paste, it would seem. So let me at least adopt some of today's lessons learned and instead do something like this. For underscore in range of 3, let's now print out just one of these at a time. But the fact that I've now used a 3 to range means if I want to change it to something bigger or smaller, I change it in one place, not in 3 or more places. And this code, too, of course, if I got it right, is just going to print out the exact same thing. So we're iterating here. But let's see if we can't now integrate our discussion of writing functions of our own to begin writing something a little more dynamic and solving more complicated problems ultimately. One of the nice things about functions is that they allow us to not just write code that we can use and reuse, they allow us to create abstractions, if you will. An abstraction is a simplification of a potentially more complicated idea. And we've seen this a few times over the course of the weeks. For instance, we had a function called hello, which granted didn't do all that much. It just printed hello, but it allowed me to think about the function as exactly what it does. Not generically printing something, but literally saying hello. I've been able to get a number using something similar by defining my own function like getNumber. Well, let me go ahead and, for instance, assume for the moment that I've had the forethought to, in my function main, use a function called printColumn. That seems as good a name as any to use a function that prints a column of bricks. Well, how can I go about now implementing this abstraction, this simple idea, print column, with actual code? Well, we've seen before with def we can do just that. Let me define a function called print column. Let me accept as its input, generically speaking, a parameter called height. I could call it n or h, but I'll be a little more explicit now with height, just so I remind myself what it's doing. And now I think I can just borrow some of that same code from before. For underscore in range of height, go ahead and print out a single hash. And then at the end of this whole program, let's just call main. So I've kind of complicated the code. It doesn't do anything more just yet, but it's setting me up for solving what I think are going to be more sophisticated problems. If I run Python of Mario.py, we're back where we began. But I now have a function, an abstraction print column, that's going to allow me to think about printing some chunk of the world of Mario at a time. And I can do this in different ways too. Notice that if I really want, I could do something like this. I could re-implement now print column in different ways, especially if I'm using print column all over my code, or maybe still a colleague of mine, a friend, someone else on the internet is using my print column function. What's also nice about functions you've written is you can change the underlying implementation details of them, but so long as you don't change the name of the function or its parameters or what it returns, if anything, no one else knows the difference. You can change the internal implementation as much as you want if you want to improve it or make fixes over time. So for instance, another way we could implement print column, recall, would be something like this. A bit clever with one hash and then a new line, and then maybe we could do multiplication of strings and then end this line with quote unquote. Again, it's okay if you're not comfortable with this syntax. This was a more clever approach we saw in the past, but if I run Python of Mario.py here, I'll still see a column of 3. But what's important here is that main does not need to know that the underlying implementation of print column has changed. Well, let's transition to a different dimension, if you will. And rather than print out just these vertical bricks, let's fast forward in the game to this part of the world here. At some part, Mario encounters these bricks in the sky that if he jumps up underneath, they become coins. And so he gains to his score. But let's go ahead and focus only on those coins. And let me propose that we print out, just these 4 question marks here. And let me go back to VS Code here. And let me propose that within VS Code here, just like before, we try to abstract this away. So let me go ahead and get rid of this version, because we're now going horizontal instead of vertical with our output. And let me just say, well, print row 4 times. Let me just abstract away the problem at hand. I don't know yet how I'm going to print those 4 question marks, but let's call it print row 4, and I'll assume I'll now solve this problem. Let's now go down that rabbit hole of solving the problem. Define a function called print row. It's going to take a width instead of a height, because it's horizontal instead of vertical. And how can I do this? Well, now we have an opportunity to do string multiplication even more elegantly. I can say quote unquote question mark times width. And this is a very pretty Pythonic way of printing what could otherwise be a loop, and that's fine. But this is going to go ahead and print those question marks for me. Let's do Python of Mario.py enter. And now I've got 4 question marks. It's not nearly as pretty as the more graphical version, but it is at least a building block toward having now a reusable function like print row. And why am I doing all this? Like, why are we over-engineering the solution to these problems by having print column and print row? Well, it's a useful problem-solving technique as soon as your world does not look one-dimensional like this, or with the column version. But what about this? Later in Super Mario Brothers, does Mario have to jump down into this world where there's a lot of these underworld barriers? And this one here, for instance, looks like a square. It's 2-dimensional. There's a height and a width to it. And that is to say, there's a bunch of different ways we could implement this thing if maybe for discussion it's like a 3x3 grid, a 3x3 square of sorts. Well, how can we go about solving this here problem? Well, let me propose we come back to VS Code, and let me propose that we think about this in a couple of different ways. I could do this like this. If I know where I'm going, you know, maybe I'm a seasoned programmer, let me go ahead and do this. Let me print out a square, the width and the height of which is 3. That's an abstraction. I'm just taking for granted for a moment that there is already a function called print square that's going to be width 3 and height 3 as well. But someone's got to implement this. And at the moment, there's only me at the keyboard, so let's go ahead and implement that square. Let me go ahead and define a function called print square that takes in a specific size, both for height and for width. And here's where we have an opportunity to use some of those loops. And we can use those loops in a way we haven't yet. If I want to print out all of these rows, but also all of these columns, I now have to think not just cyclically, like a loop allows, but I need to think 2-dimensionally. And if you're familiar with like an old school typewriter, or even a printer nowadays, it generally prints from top to bottom. So even if you have multiple columns, you print out one line at a time. And while you're on that line, the printer or the typewriter prints from left to right. And that's kind of the mental model to have with your black and white terminal window. All of the output for every example thus far starts at the top and goes down to the bottom, from top to bottom, left to right. So we have to generate our output, our square, in that same way. So let me propose that we do this. Let me propose that we know we need to iterate this many times, 3 or more generally size. So let me do this. For I in the range of size, what do I need to do 3 times? Well, I want to print out what? 1, 2, 3 rows of bricks. But within each row of bricks, what do I want to print? 1, 2, 3 bricks specifically. So if we go back to our diagram here, and I stipulate that it's indeed meant to be a 3x3 square, 3 wide and 3 tall, what do I want to do to print the first row? I want to print brick, 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 brick. What do I want to print on the second row? Brick, brick, brick. And the third row, brick, brick, brick. So I'm doing 3 things 3 times. There's a lot of printing that must happen. So let me go back to my code here and let me propose now that we think of this outer loop that I've just started as representing each of our rows. For I in range of size is going to ensure, no matter what I do next, that I can print out 1, 2, 3 rows. Or more generally, size, where size could be 3, but it could be smaller or larger. What do I want to do on each of the rows? Well, just like an old school typewriter or printer, on each row, I want to print out brick, 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 brick. Well, that sounds like a cycle, some kind of loop. So maybe I can have inside of one loop another loop. I don't want to use I again because I don't want to use the same variable and mess up my counting. So I'm going to, by convention, use j. Very common to use I and then j, maybe k. But after that, you shouldn't keep nesting inside of each other. Let me go ahead and say for j in range of size 2, because it's a square, and then each of these rows, let me print out a single hash, but no new line. But after each row, let me print only a new line. So there's a lot going on here, especially if you've never touched Python, let alone loops. But notice what I've done here too, and I'll add some comments for clarity. For each row in square, for each brick in row, print brick. And here is where comments, and more generally pseudocode, can really help explain to yourself and to others what your lines of code are doing. On line 8, I'm iterating from I equals 0 on up to size, so 0, 1, 2. On line 11, I'm doing the exact same thing but using j from 0, 1, 2. But that's good because I represents now each of my rows, and while I'm on each of those rows inside of this outer loop, I'm going to do brick, brick, brick. 1, 2, 3, 1, 2, 3, 1, 2, 3. But I don't want my cursor to keep moving to the next line while I'm on a row, so I'm just overriding that line ending. But let me ask a question of the group now. Why on line 16 do I have a print here all by itself? Why do I have a print all by itself? Notice that it's below the inner loop, but inside of the outer loop, so to speak. What is that loop on line 16 doing ultimately?
Every time you finish a line, you have to add a new line at the end of it. So
Perfect.
it prints a new line.
Perfect. I don't want a new line after every brick. I only want to do that at the end of the row, and that's why my comments now are perhaps enlightening. Notice that this loop here is just iterating for each brick in the row. Once I'm done with that inner loop, so to speak, once I'm done with these highlighted lines here, to Evelyn's point, I need to print out one blank new line. And we've not done this before, but when you call print with no arguments, all you get is that automatic line ending, the \n, where the cursor moves to the next line. So if I now go back to my terminal window and run mario.py, I think I should get a 3 by 3 square. And it doesn't quite look like a square on my screen because these hashes are a little taller than they are wide, but it is in fact 3 by 3. But let me propose, as we've always done here, how we might tighten up this code further. Just for clarity's sake, let me get rid of my comments for a moment, just so we can see how many lines of code we have total. And let me propose that we maybe do this. Let me propose that, you know what, this inner loop, especially if you're having trouble wrapping your mind around one loop inside of another loop, you don't strictly need it. What if we do this trick again? What if we print out inside of the outer and only loop each of those hashes times the number of times we want them? Right? We draw inspiration from an earlier approach and we run Python now of mario.py, same result, but now print square is really nice and compact. It has one explicit loop, and it's still printing out using string multiplication all of the hashes at once on that row. If you like abstraction and you'd like to wrap your mind more around what the code is doing, well, let's do this. If you're not quite clear on what's going on, let's propose that you implement a function called print row, passing in size. And let me propose that this print row function, it simply take in that width and print out the individual hash times that many times. In other words, here's an opportunity for abstraction, whereby, well, what does it mean to print a row? Well, when you're implementing print square, I don't really care what it means to print a row. I just need to know that someone's taking care of printing the row. You can kind of pass the buck to another function altogether. And how does print row work? Well, it could use a for loop. It could use this string multiplication trick. This is a way to take a larger program, and this is probably the most complicated one we've looked at thus far, and to decompose it into these smaller components that, once assembled, achieve your final idea. Seeing no questions, that's the end of our look at loops in Python, this ability to do things cyclically again and again. And when we combine those with conditionals, this ability to ask and answer questions and combine them with our functions and variables, we really now have most of the building blocks we need to solve much larger, much more interesting, much more personal questions. So in the weeks to come, we'll start to see exactly what could go wrong, though, when we do so. But we'll introduce you to all the more tools via which you can troubleshoot those same problems.
Well, hello one and all, and welcome to our short on dictionaries. Now, dictionaries are useful when you want to store similar kinds of information in terms of these key value pairs. So more on that in a moment, but let's first dive into our scenario here. I have here a program called report.py where the goal is to write a report on some given spacecraft that's out there in the universe. And notice how here I have a function called createReport that takes as input something called spacecraft, an argument here called spacecraft. And my goal is to, well, one, hopefully make sure this report actually has the information I'm looking for, and then return that report for printing, perhaps up in main over here. Now, we said that dictionaries are good for storing collections of related information. And I think a spacecraft kind of qualifies in this sense. A spacecraft has something like a name, maybe like a distance from Earth, let's say. So I think a spacecraft could be good to represent with a dictionary. Well, let's try this out here. I'll go ahead up to main here, and I will create our very first spacecraft that I'll call, in this case, just spacecraft. And I'll set spacecraft equal to, well, a dictionary. And so we've seen that a dictionary begins with these curly braces, whereas a list begins with square brackets. A dictionary is denoted with these curly braces here. Now, a dictionary, of course, comes with these keys and values. Now, a key is simply some name, so we're accessing some particular value inside of this dictionary. And maybe the first key we should have here is some attribute of our spacecraft, maybe its name, for instance. So I'll say here, one of our keys is name. And syntax-wise, what I have to do when I specify a key is this. I give the name of the key. In this case, the name of the key literally is name. I can then type colon followed by the value I hope for this key to represent. So in this case, maybe let's talk about Voyager 1, which is the furthest man-made spacecraft, really any kind of object away from Earth, Voyager 1 here. So here, our spacecraft is a dictionary, and we have one key, name, that is assigned the value Voyager 1. But of course, there are more really properties of Voyager 1 we can actually put inside of this dictionary. One of them is distance. Distance. And we said Voyager 1 is the furthest man-made object from Earth. So we'll go ahead and say that this is 163 astronomical units away, which is on the order of, I would say, billions of miles away. Go ahead and look up what that conversion is on your own. So here we have Voyager 1, and we also have a distance of 163 AU. And this together forms our spacecraft. So if I want to create a report on this spacecraft, I could, as we said before, maybe print the result of create report, but then give as input our spacecraft down below. And hopefully, if we run python report.py, well, we see a report. Like I argue that create report is returning us some text. text, and we're printing it in main, but we haven't fixed these to-dos. So we have here our own dictionary with keys and values that we have specified. But if we want to access those values given some key, well, we can do that perhaps in create report. Now, in general, we could assume, let's say, that create report is given some spacecraft that is a dictionary with these two keys, name and distance. And the goal here is really to just access the values at those keys. So I could use here our Python f string and use curly braces of my own. These are not curly braces for a dictionary. These are curly braces for interpolating some value. I can put in Python code here to get some value and actually incorporate it into this text called report here. So for the name of our spacecraft, we know we have a dictionary that's called spacecraft being passed as input to create report. And we also know, or we can assume in this case, that this dictionary will have a key called name, all lowercase. So to access the value at this key, we can use brackets followed by the actual key of our actual name of our key. In this case, the name of our key literally is name. So here, to be clear, what we'll do is go ahead and interpolate some value inside of this f string, and this value will be the value we access by accessing the name, the key name, as part of our spacecraft dictionary here. Let's do the same thing now for distance. We can assume that our spacecraft dictionary also has a key called distance, just like this. And now, if we were to rerun this report, I think we'd see that we get a report back with our name being Voyager 1 and our distance being 163. But there are no units here, so let's go ahead and actually add this in. 163 AU, or astronomical units. All right. So this is our report. And you can kind of get a sense for how handy these things like dictionaries can be. We are able here to combine various pieces of information, the name of our spacecraft, the distance, and then access it very easily using these keys that we have down below. Now, what might go wrong with dictionaries? Well, let's say we're not using Voyager 1 anymore. We're using a new spacecraft, or more specifically, a kind of telescope called the James Webb Space Telescope, one of the most recent space telescopes created that can help us see far beyond in the reaches of space. So here, I'll make a new dictionary, and I'll set the name to James Webb Space Telescope. But I'm actually not quite sure how far away this telescope is from Earth, so I'll leave that key empty here. Well, I can go ahead and try to run Python of report.py, but before I do, maybe think about what might go wrong when I call create report. Let's see here. I'll hit enter, and I'll actually get what's called a key error down below. I see key error : distance. And it seems to me that we tried to access this key named distance in create report, but our assumption was not quite correct. Spacecraft does not have a key called distance. So let's go ahead and add that key here. Well, it turns out that to add a new key to a dictionary, I don't need to just simply create it as a dictionary is being built. I could also do this. I could go ahead and try to do spacecraft bracket distance, much like the syntax down below, to access this key, but then supply some value. In this case, I could say that it is, I think, let me just check here, it is 0.01 AU away from Earth. So actually, interestingly, the James Webb Space Telescope kind of orbits the sun in a kind of constant distance around from Earth, so about 0.01 AU here. Let's go ahead and run this report again. I'll say Python of report.py, and now we'll see that our report has been fixed for us down below. Okay, so we've seen here various ways to add keys to dictionaries, various ways to access those keys and to create our own dictionary. Let's consider more ways to actually access these values for a given key. Let's go back a little bit and assume we actually don't have this value, 0.01. We have just here the key name. What could we do to perhaps maybe anticipate this error and make create report a little more flexible with the kinds of input it might get? Well, it turns out that to access some key, we don't need to always use this bracket notation. In fact, there is some other method, one called get, we can use to try to access some key. And if that key doesn't exist, we'll actually get some other value we specify instead. So here, perhaps in distance, I could, instead of using bracket distance here, I could use dot get, so the name of my dictionary, spacecraft, dot get, followed by the key I hope to access in my dictionary, in this case, distance. I could, if I wanted to, supply another value that will actually be returned if this distance key is not part of my dictionary. And we saw earlier that distance is not part of this dictionary, so what we should hopefully see instead is unknown. Why don't I go ahead and try Python of report.py, hit enter, and now we'll actually see that get returned to us unknown instead of the actual value for this non-existent key. And this avoids the key error we saw earlier as well. So let's try this here. I'll do spacecraft.get, and I'll try to get the name of the spacecraft. Otherwise, we can go ahead and return unknown as well. So in general, you'll find that most of the time you can use that same bracket notation we saw earlier, but if you aren't sure if some key will exist, you could use get to try to get that key, but return some other value if that key, in fact, does not exist inside of your particular dictionary in this case. So I believe this gives us an example of how we can go ahead and get our keys. Let's now explore other ways to add keys beyond just the same syntax we saw earlier as well. So recall, we could go ahead and add in a key by creating our dictionary up here. I could say distance, distance colon, etc. here. I could even do some syntax like this, spacecraft distance equals, let's say, 0.01. These are two ways to add keys to a dictionary. Turns out there's also one more to be familiar with as well. If I wanted to add not just one key at a time to my dictionary, but maybe multiple at once, I could use a method called update. So I could type the name of my dictionary, followed by a dot, and then update, just like this. And update takes as an argument, as an input here, another dictionary, but it will really take that dictionary's keys and values and just add them to the dictionary I started with here, in this case, spacecraft. So it will update spacecraft with all of the keys and values that I provide as input to update. Now I could go ahead and specify here in another dictionary, maybe the distance, which we said before was 0.01 AU, and then we can maybe specify another attribute, maybe the orbit here. As we said before, the James Webb Space Telescope orbits the sun in this case. So here I'm trying to add now two new keys, one called distance and one called orbit, each with their own values. And I could also go down below here and I could add in some new line in my report. Maybe I'll say orbit, and that is equal to maybe spacecraft.get, the key called orbit. Otherwise, we'll return unknown if that key perhaps doesn't exist down below. All right, so here we've tried to add here two new keys at once to our dictionary up above. Let's go ahead and run python report.py, and now we'll see that those keys are in fact part of our dictionary thanks to update as well. So now we've seen how to add keys in various ways, how to access keys in various ways, but let's see some other utility features of dictionaries as well. I'll actually go ahead and remove what I have here, and why don't we try to make a new program, one called distances.py. Now in distances.py, we're going to treat dictionaries a little bit differently. I'm going to make a dictionary where I have the names of my spacecraft in one column, if you will, and the distances of those spacecraft in another column, if you will, of my dictionary. So for instance, I can make a dictionary called distances and open up some curly braces here. And as the keys in this dictionary, I'll go ahead and have the names of spacecraft, like Voyager 1, for instance. Now the value of this particular key will be the distance that Voyager 1 is away from Earth, which happens to be 163 AU, as we saw before. Now I can go ahead and add other keys to my dictionary, other spacecraft and their distances. I could also go ahead and add Voyager 2, which happens to be 136 AU away from Earth. I could go ahead and add Pioneer 10, which is about 80 AU away. New Horizons, another probe, which is about 58 AU away. And finally, Pioneer 11, which is about 44 AU away. So notice how here my dictionary is representing multiple spacecraft, but I'm really defining the relationship between my spacecraft names and their distances as well. So with my information represented like this, I could try to maybe print out each of their names and their distances using some key functionalities of dictionaries here. I'll go ahead and define myself a function called main, and I'll leave that empty for now. I'll go down below and make sure I call main. And now within main, my goal is to, for each spacecraft I have inside of this dictionary, print out its name and the distance away from Earth. So if I want to do something for each, let's say, anything I have, a good idea is to use a for loop. In this case, I want to do something for each key I have in my dictionary. Well, it turns out that dictionaries come with a method called keys that returns to me all the keys in my dictionary. So I could type for name in distances dot keys. And again, dot keys, this method here, that will return to me all of the keys in my dictionary. So first Voyager 1, then Voyager 2, then Pioneer 10, New Horizons, Pioneer 11. These will all be part of the return value of dot keys when called on the distances dictionary. And now I'm saying for name in that list of keys. So first name will be equal to Voyager 1, then Voyager 2, then Pioneer 10, as my for loop continues in the code indented here on line 12. So now that I have name, which will first be Voyager 1, Voyager 2, I might also want to access, in this case, the distances of those probes from Earth. And to do that, I could actually maybe plug in my key to my dictionary and get back the value I'm looking for. Let's demonstrate this here. I'll type print, and I'll use an F string. And I'll then say name, referring to the name of my spacecraft, is, and then some distance away from Earth. But again, we have here name, which is in fact a key of our dictionary. So I could type distances, bracket name, to access the value for each of these various keys I'm getting. For instance, when name is equal to Voyager 1, I'll get back 163 right here. When name is equal to Voyager 2, well, I'll get back 136 right down here. So I could complete the sentence by saying name is some distance in AU from Earth, just like that. Let's go ahead and try running this. I'll say Python of distances dot .py, and we'll see here some other reports on our spacecraft. Voyager 1 is 163 AU from Earth. Voyager 2 is 136 AU from Earth. So when you want to do some kind of code like this on line 12 for each key in your dictionary, you could use dot keys to access each of those keys and loop over them perhaps with something like a for loop. One more to be familiar with here. We can also loop over, let's say, the values in our dictionaries. So just like we have keys, we also have values as well, dot values. And let's try maybe converting these AU to meters instead, a much more friendly unit of measurement. So I'll go ahead and replace this code down below here, and why don't I actually delete this for loop here, and first give myself a function to convert AU into, in this case, meters. And it turns out that the number of meters corresponding to 1 AU is this big number here. I'm not even sure how to pronounce it, but I will make sure to type it in correctly. 597870700. And I believe this is correct. 870597149. Yes, this really big number that I don't know how to pronounce is the number of meters in one given AU. So if we wanted to perhaps loop over all of our values in the dictionary, so first 163, then 136, then 80, and so on, we could use a for loop. I could say for, perhaps distance, in distances dot values, and then I could perhaps print, using an f string, the distance in AU is the converted distance in meters. So to be clear here, a function called convert that takes a single amount of AU and converts it to meters. Then, in main, we go through each value in our dictionary's values, and then we'll go ahead and convert that distance to meters and also print out the distance in AU. So I'll go ahead here and I'll run Python of distances.py, and now we'll hopefully see down below all of these distances in AU now in meters. So we've seen a lot about dictionaries. We've seen, back in report.py, how to create them, how to supply keys and values. We've seen how to update our dictionaries, whether using the update method or by using bracket notation we saw a little earlier too. We've seen how to access those values given some key. We've seen the get method down below, as well as the more simple bracket notation too. And over in distances.py, we've seen how to loop over the keys and the values in our dictionaries. That's it here for our short on dictionaries. We'll see you next time.